The purpose of this video is to provide a makeup for what we did in the week 29 class. Our topic today was Introduction to Waves, and just here's a cartoon to get us going. Should have put this a few weeks ago. Okay, in the notes handout you'll see there are 6 major points that we are going to cover in this lesson. What is a wave? What causes waves? What are some types of waves? What are some characteristics of waves? What determines the wave speed? And what happens when a wave reaches a boundary? So point 1, what is a wave? A wave is a disturbance that transfers energy across a distance without transferring matter. And we just looked at a couple examples in class. We used a slinky to send energy from one person to another, but the actual coils of the spring did not move from one person to another. And likewise with a sound wave, when you talk, the air molecules get bumped, and then they bump into the next air molecule, and they bump into the next one, and eventually they bump into somebody's eardrum. But the air molecule that was initially caused to vibrate by your vocal cords is not the same air molecule that was at your friend's ear. And earthquake waves are another example. Point 2, what causes waves? Waves are caused by a vibrating object, and these are some of the things we illustrated in class, although we did not illustrate the earthquake waves. We looked at, let's see, so wave pulse on a spring, obviously you vibrate the end of the spring, and that sends a wave down the spring. This was a cup attached to a string attached to a hanger, and if you hold the cup at your ear and you let the hanger bang on something, it sounds like a church bell. So there we have the hanger is the vibrating object, and then those vibrations get transmitted through the string to the cup to the air to your ear. Talking tape is a little plastic strip with ridges on it connected to a cup, and you listen in the cup, and if you pull your fingernail over the ridges are done just right so that the vibrations will be the same as somebody talking and saying some different words. So we went through all these and just different examples of what's vibrating. A record player, the grooves are made such that they will create the vibrations necessary to replicate the sound. And we took a record player and put, instead of using the arm and the needle that come with it, we had a needle, just like a sewing needle, taped to a paper cone, and we put that needle in the groove while the record player was on, and you could hear the music coming out the paper cone. Point 3, what are some types of waves? So the first type we're going to look at is transverse waves. And in a transverse wave, the particles of the medium move perpendicular to the direction the wave is traveling. And 2 examples of these are the secondary waves produced by earthquake and waves on the strings of instruments like a piano or a violin. And this picture shows what we're talking about here. This is a diagram that you'll see in the simulation. This is supposed to be a rope, so it's showing all the particles on a rope or a string. And this blue arrow is showing that as the wave travels from left to right, the particles only go up and down. So this particle will only have an up and down motion, but the red arrow shows that the wave is progressing to the right. These kinds of waves can only occur in solids, and that is because in order to have a transverse wave, each particle needs to pull up or down on the particle next to it, and that's only possible in solids. Longitudinal waves. So here we have the particles of the medium move parallel to the direction the wave is traveling. So here we have this longitudinal wave moving to the right. This is a diagram from Dan Russell, and you can go to this website to see it in motion. It's pretty neat, so I really recommend looking at that. This would be, for example, these could be air molecules. This could be a sound wave. And the crests of the wave are the places where you have the higher density of air molecules. And this wave is traveling to the right, but an individual particle only moves a short distance right and left. And these can occur in solids, liquids, and gases. And I really do recommend looking at that website. Point 4, what are some characteristics of waves? So first of all, we're going to look at the amplitude. Amplitude is the distance from the equilibrium position to the maximum displacement. It is related to the amount of energy in the wave. So here, this dotted line here is what we would call the equilibrium. That's where the rope would be if it was at rest. And when you have a wave on it, you'll notice that there's peaks that are above the equilibrium and troughs that are below. And the amplitude is the distance from that equilibrium to the crest or the equilibrium to the trough. Those distances are equal. For sound waves, the amplitude determines the volume of the sound. And for light waves, the amplitude determines the intensity or brightness. The speed of a wave is the distance traveled by the disturbance per unit time. And the disturbance you can think of as the movement of the energy. It's what's holding the energy. If you just have a single pulse, just a single lump in your wave, you just yank that rope one time real quickly, then you would just look at how far did that pulse travel in how much time, and that would give you the speed. Or if you have a oscillating wave like this that's continuous, you can just look at the distance traveled by one point on the wave over time. So you could look at, the crest is here right now. How much time does it take, to go 10 centimeters? And then take distance divided by time to get the speed. So now we're going to do exploring waves on a string. These are old instructions here, so don't do this. Just use the link in the folder to open the simulation. And also the simulation that you'll be using looks a little bit different. They've updated their simulations to use HTML5, so just follow the instructions here, but the visual will look a little bit different than what you see here. So set it to manual and set it to no end, which basically means you need the wrench and the window. And then play with it and see if you can accomplish each one of these tasks. So in class I was able to check and see that people were able to do each of these things. Go ahead and pause this presentation, work with the simulation, and make sure that you can do these different things. Let me know if you have any questions. And part 2 of this one. Okay, hopefully now you have had a chance to finish accomplishing all these tasks. And what you hopefully found out, I'm going to check our results here. Hopefully what you found out was that if the tension is high, the speed of the wave was about 6.2 centimeters per second. And when the tension was medium, the speed was around 3.8 centimeters per second. We found that the amplitude did not affect the speed of a wave pulse, and we found that the damping also did not affect the speed of the wave pulse. So from this, we can see that the tension affects the speed, but not amplitude or damping. Okay, next we will look at wavelength. Wavelength is symbolized by the Greek lowercase letter lambda, and it's the distance between two similar points on a wave. And two similar points could be two crests, that would be a wavelength, or two troughs, that would be a wavelength, or here I have started with, the fourth particle up from the trough, and I went to another fourth particle up from the trough. So all of those are the wavelength, they all would be equal to each other. Frequency is symbolized by the lowercase letter f. It is the number of cycles per second. And the units would be 1/seconds because it's cycles per second, but cycles doesn't really have a unit, that's just a pure number. So the units are 1/seconds or 1 over any other unit of time. And 1/seconds is what we call a hertz, H-E-R-T-Z, abbreviated capital H, lowercase z. So the units of frequency are most commonly expressed in hertz. Frequency is the number of vibrations or cycles made by the source or a particle on the wave in 1 second. Another way of thinking about it is that it's the number of waves that pass a single point in 1 second. So you can either focus on what the source or an individual particle is doing, or you can focus on a specific place and how many waves go by in 1 second. And how do we experience different frequencies of sound waves? Well, that's going to be the pitch. So a higher pitch is going to have a higher frequency. And for light waves, that is going to be the color of the light. So another simulation, things that we practiced. So go ahead and set it up with these criteria, and then make a periodic wave that has a low frequency. So try 1 hertz. So what we did there was we jiggled the wrench so that it would take 1 second to go up, down, and back to the equilibrium. And a periodic wave means that it's repeating. So you would be going, starting here at the starting at the equilibrium, which is actually down here, you would be going up, down, up, down, up, down, up, down, up, at a rate of 1 complete cycle every second. And then try a high frequency and notice how they look different. Then do a periodic wave that has a long wavelength and a short wavelength. And then point 3, how does changing the frequency affect the speed of the wave? So try changing the frequency and calculate the speed and see if how it compares to what you found previously. Okay, now that you've had a chance to try those, hopefully you found that as you increased the frequency, the wavelength got shorter. And how does changing the frequency affect the speed? It should have had no effect on the speed. Then we played with the oscillating setting and made a periodic wave that had a wavelength of 5 centimeters. So play with the frequency until you get a wavelength of 5, and then change the frequency and get something that has a wavelength of 2.5. And there's the rulers you can use to measure that. 2, how does changing the frequency affect the amplitude? So take a look at that, and then take a look at number 3. When you're done, check back. Okay, hopefully you found that changing the frequency does not affect the amplitude, but changing the frequency does change the wavelength. And if you increase the frequency, it shortens or makes the wavelength smaller. Period is symbolized by capital T, and that's because it's a very special time. It's the time for 1 cycle. And you can once again consider either the source or particle, or you can look at a whole wave. So if you're looking at a source or a particle, the period is the time it takes for the source or an individual particle on the wave to complete 1 cycle. Another way of looking at it is that it's the time it takes for 1 wave or 1 wavelength to pass a single point. Now, in your notes, the way I put down the definitions for frequency and period is that both ways of looking at frequency are together, and both ways of looking or thinking about the period are together. Here, what I've done is just rearrange those so that you can see how to think about frequency and period based on what you're looking at. For example, if you are looking at the vibrating source or a particle on the wave, then frequency is the number of vibrations made by the source or particle in 1 second. And the time is the time it takes for that source or particle to complete 1 full vibration. However, if you are looking at the resulting periodic wave, then frequency is the number of waves that pass a single point in 1 second. And the period is the time it takes for 1 full wave, meaning 1 wavelength, to pass a single point. So then we did another simulation, and we set it to oscillate, and we set the frequency to 2. And go ahead and take time now to go through these and measure these things and verify that you're coming out with what you would expect to come out with. So for example, when the frequency is 2 hertz, how many vibrations does the source make in 1 second? So measure it and see what you get. But 2 hertz means 2 cycles per second. So the source should make 2 full vibrations in 1 second. And you can use the little clock feature to measure that. Then we looked at how are period and frequency related to each other. So suppose 2 vibrations occur every second. How much time does it take for 1 vibration to occur? Well, logically, if 2 vibrations happen every second, then each one takes half a second. So the period would be 1/2 second. The frequency would be 2 because number of vibrations per second is 2. You'll notice that those are reciprocals of each other. That if the frequency is 2 hertz, which is 2 over seconds, if you flip that over, you get half a second. So I'm not going to write it here, but we wrote a short little equation, I guess you could say, that period equals 1 over frequency, or frequency equals 1 over period. They are reciprocals. Step 5, what determines, meaning causes or affects, the wave's speed? This is really important, and some of this you've seen already in the simulations. The speed is determined by properties of the medium. What has no effect on the speed? It's a lot of all the other things we looked at: frequency, period, wavelength, amplitude, and damping. So this is really important to remember. The speed is determined by properties of the medium, not how the vibration is started. So if you think about a spring that you have stretched between 2 people, there's a certain amount of tension based on how far they have, pulled that spring. The tension is a property of the medium. Now one of the people start jiggling the end of the spring. They could jiggle it with all different kinds of amplitudes, of different frequencies. There could be different amounts of damping. All those things don't affect the speed. The speed is determined just by what the spring is made out of and what kind of tension is in it, and so forth. So then we put down 3 equations for the speeds for these different types of waves. For the speed of the electromagnetic wave, we had already that the index of refraction equals c over v. So the optical density affects the speed of light waves. For speed of sound in air, I will put that equation in the instructions for the makeup document, and the speed of the wave on a string, I'll also put that equation there. Then we did these 2 practice problems, so go ahead and try those. I'll put the answers in that instructions document. And then we did the spring lab. Go ahead and hopefully you've printed that out already. I have included on there the data that we took of the distance and the times, so you can calculate the average time and calculate the speed of each wave. Step 6, what happens when a wave reaches a boundary? Now this follows up on what we saw with the spring lab. We watched the wave reflect, and so here you get a chance to do it with the simulation. So in the simulation, set it to fixed end, which should be a clamp, and then send a pulse and watch that upward pulse. Watch what happens when it reflects from the other end. Does it come back also upward, or does it invert and come back on the bottom? So try that, and then try it with a loose end. And hopefully what you saw was that when a wave reaches a fixed end, it reflects and its orientation is inverted. And then when you get to the loose end, it reflects and the orientation stays the same. And step 7, what are the characteristics of this wave? So here what I want you to do is figure out all of these with these settings. Now it used to be more difficult with the old simulation because they didn't actually give the amplitude and the frequency. So amplitude and frequency you can fill in right away, even though there's no equal sign over here, there should be. and then measure the wavelength, measure the period, measure the wave speed, and then you will have completed the week 29 class.